Welcome to Probability and Statistics. In this lecture video, we're going to talk about one particular discrete probability distribution, which is called the binomial distribution. Alright, so binomial probability distribution is a specific type of discrete probability distribution. Alright, so let's take a look at the property of what we so-called a binomial distribution. The experiment, okay, for this type of distribution consists of a fixed number, lowercase n, of identical trials. Each trial is independent to the other trials. For each trial, there are only two possible outcomes. And this is the key for being a binomial distribution. One outcome labeled as success, the other outcome is labeled as failure. Alright, so probability of getting a success is called the P. Probability of failure is called 1 minus P. And sometimes I will use the letter Q for probability of failure. Just a, less letter to write. Alright. So the binomial random variable X counts the number of success in n trials. So the letter X for your random variable representing the number of success. Alright, P is a probability of success, Q is failure. Alright, the X, the variable X representing the number of success. To find the mean, alright, for binomial distribution, the mean is always given by n times P. Alright, how many experiments, number of trial times probability of success. And the variance is given by sigma squared, which is n times P times 1 minus P over Q. So at the same time, if I want to find the standard deviation of my binomial, that would just simply be the square root of n times P times Q. Alright, so I'm gonna just remind you that on the formula sheets, okay, this test, you got to begin to really start using the formula sheet. So we're in chapter 5. So if you look at the formula sheet for chapter 5, alright, we got our expected value, which we learn how to find them, which we learn how to find them in the calculator. So for binomial distribution, okay, it will be n times P for probability of success. Let me see if I can find it in a little bit nicer place. You can use the chapter 6 right here. Normal distribution, approximation of binomial distribution. Mean is n times P. Standard deviation is right here. So it's the same thing. So when we get to chapter 6, alright, we're going to talk about something called a normal distribution approximation of a binomial. So here is your mean and your standard deviation. So a lot of these formula, we will begin to see them over and over again. So I just want to point out where the formula is at. Alright, so let's do an example. The random variable X is a binomial random variable with the number of trial is 10, probability of success is 0.1. What's the expected value? So the expected value, okay, is your mean, mu, which is n times P. Alright, so my n is 10. My n is 10. P is 0.1. So that will just be 10 times 0.1, which will just be 1. So my expected value, or my mean, would just be 1 for this problem. Alright, so let's take a look at the computation of how do we compute the probabilities, okay, of binomial experiment. So before I do that, I want to go over this problem, kind of guide you a little bit, make you help you understand the formula. So let's pretend Mr. Chen is a 75% free throw shooter. Find the probability that Mr. Chen made exactly 3 out of 5 free throws. Made exactly 3 out of 5 free throws. Alright, so I'm going to shoot 5 free throws. So I'm going to say, let capital letter M representing make the shot. Alright, lowercase m represent miss. So if I'm gonna shoot a free throw 5 times, I need to make exactly 3. So that means I can make the first one, right? I can make the first one, miss the second one, make the next 2, and miss the last one. So this is one way, alright, I can make the 3 shots. I could, so I want you to understand this, I could do different things. I could make the first 3 and miss the last 2. So that's another way to make exactly 3 out of the 5 free throws. So that means what that tells us is I have 5 free throws, choosing to make 3 of them, because I need to make exactly 3. Alright, so the 2 ways I listed, okay, when I make a free throw, that would be 0.75, right, because I'm a 75% free throw shooter. If I missed, there's 0.25% chance I will miss a shot. Make is 7.75. Make is 0.75, and miss, chance of missing is 0.25. So 75% free throw shooter means I have 75% chance making the shot, 25% not making it. So one task followed by the other, we will multiply. So that's the same thing as saying 0.75 times itself 3 times 0.25 times itself 2 times. Now, what happens if I will go with a different way of making the 3 shots? Make is 0.75, right? Make again is 0.75. Make again is 0.75. The miss is 0.25. One task followed by the other, we will multiply. So basically, all these many different ways I can make the 3 shot. My probability of making it versus missing it is going to be the same for all these ways. So that's reason why for me to figure out, okay, what's the probability for me to make exactly 3 out of 5, there should be 5 choosing 3, okay, ways for me to make the 3 shots, right? And I should have well, if I do 5 choosing 3 real quick, five choosing 3 is 10. So that means this should be 10 different ways for me to make this shot. Okay, so every way has the same probability. So that will be 5 choosing 3, which is 10, okay, times, and the reason why I multiply because every way has the same probability, which is 0.75 to the third power times 0.25 to the second power. I should have 10 of these. 1, 2, plus the other 8 ways. Every one of these ways has the same probability. It's a computation part is all the same. So I actually need to add up all the 10 different ways. So rather than add this same thing 10 different times, I can just multiply by the 10. So 5 choosing 3 is 10 times 0.75 to the third times 0.25 to the second power. So the chance for me making exactly 3 free throws is about 0.2637. So that will be about 26% chance making the free throw. Alright, so what I just did is exactly what this formula is describing. Alright, so for a binomial random variable x, okay, the probability of obtaining x number of success in n independent trial is given by probability of the random variable x is equal to the combination of the number of trial times number of success times probability of success raised into the number of success power times the probability of failure, which is my 0.25, to the second power, n minus x. So this is a binomial problem is because I will either make a shot or I will miss a shot. So binomial always has that sense of success and failure. I want to make exactly 3. So the number of success I want is 3. So therefore the number of failure is 2 because I only got to shoot 5 times. Alright. So when we read probability questions, and we've been talking about this for a bit now. Alright, these wordings very important now. Okay, at least, no less than, greater than or equal to is using greater than or equal to symbol. Okay, more than, greater than is just without the equal sign. Less than, fewer than is less than. No more than or at most is less than equal to. When they say the word exactly, that's using the equal sign. Alright, so rather than using the formula here, okay, I'm going to show you how to do this in the graphing calculator. Alright, but in the graphing calculator you need to understand 2 things here. Something called the CDF. CDF representing what we so-called the Cumulative Distribution function. It can easily be used for computing probability involving with less than or equal to. Alright, less than or equal to, use the CDF. PDF means probability density function. This can only be used for the word exact. Alright, so if the problem does not say exact, you got to use CDF. So the word cumulative distribution, cumulative, the last time we talk about this word cumulative is probably back in section lecture video 2.1. As you can recall, the word cumulative is the sum of all the frequencies. When we say the word cumulative frequency, that's referring to the frequency of a given class and all the previous one. It's accumulating from the beginning to where you want to stop at. Alright, so that's the same concept as this word cumulative distribution. And I will show you as we go along, telling you exactly what's going on with the word cumulative. It's really thinking about, okay, everybody before. Okay, everybody before where I want to end at. just like the word, just like the example we did before, when we trying to, tossing a coin 5 times. What's the probability of getting? What's the probability of getting heads? So if we go back and look at the example we had before, back in 5.1, I think it's a question about 5 heads. Toss a coin 5 times. Alright, toss a coin 5 times, and we want heads. So each one of these, okay, is a probability, 0 all the way to 5 head. So cumulative means if I want to say no more than 3 heads, so that will be adding the probability no more than 3. That will be adding all the probability from before, okay, and the probability the one that's from before, okay, not these numbers. These numbers, remember, these numbers come from after the heads, the x times the probability, no more than 3. So that's adding everybody before, from 0 all the way up to 3. So that's the word cumulative. All right, and we'll begin to see problem like that. We'll begin to talk more about it. So just remember, when the problem says the word exact, you got to use PDF. So how do you find the binomial CDF or the binomial PDF? We're gonna go to this place called second vars. If you press second vars, that's referring to the word distribution. Alright, go up until you see something called the binomial CDF and PDF. So when I go up just now, I'm actually starting from the very bottom. So here is your CDF and the PDF. And what we're gonna enter is N, P, and X. Number of independent trials, probability of success, and the number of success. So you need to memorize what you were supposed to type in the parentheses. So if I will go back to the problem we just did about my free throw, the word exactly 3. So that would be binomial. So another way to find this, rather than using a formula, binomial exact will be using PDF. BINOM PDF. And what I type in inside the parenthesis is N, the number of trial, which is 5 free throw, comma, P, NPX, probability of success. Probability of me making a shot is 0.75, comma, X, number of success. I want to make 3 shots. So this is what I will type in. So we select PDF, number of trials is 5, comma, probability of success 0.75, comma, 3. There you go. Same answer, 0.2637. All right. So let's try one here. So assume a random variable x has a binomial distribution with a given probability of obtaining a success. Alright. So when they use the equal sign, probability of random variable x is equal to 6. Equal means the word exact. If you actually look at my symbol with the wording, okay, exact will be equal. So I want to find out what's probability of exactly 6 success. Number of trial is 8. Probability of success is 0.5. So I'm just going to copy this real quick if you don't mind. Alright, so this is going to be binomial PDF because I'm doing exact. Number of trial is 8. Probability of success is 0.5. number of success will be 6. So what's my probability of getting exactly 6 success for this example? Second distribute probability PDF 8, 0.5, 6. Right, round to 4 decimal place. That will be 0.1094. 0.1094. Okay, and that's my answer. Well, almost 11% chance. Alright, so the next example. Same thing, but this time is doing less than 3. Alright, so I got 4 trials. I'm going to write this down for you, okay? I got 4 trials. 0, 1, 2, 3, all the way up to 4. And what I want is less than 3. My number of success got to be less than 3. So that means what I want is from 0 all the way to 2. Because it says less than. So that's what I want. So what I want is 0, the scenario of 0, 1 success, or 2 success. So for less than, okay, so for less than, I got to use CDF, Cumulative Distribution function, okay, because I'm accumulating the probabilities, okay, from 0 all the way up to 2, not 3, because I actually don't want 3. So this one is going to be Binomial Cdf. My number of independent trial is 4. And the reason why I'm using binomial because the problem says the random variable x has a binomial distribution. That's why I'm using this. Probability of success 0.7. So number of success. This is the only part student can trip up on. The number of success. A lot of students will put a 3 right here, but you actually do not need to put 3 because you don't want 3. What you want is from 0 all the way up to 2. So here I need to put 2. So what the calculator will do is find the probability of 0 success, 1 success, and 2 success, and you will actually go ahead and add them up for you. Okay. So let's give a try. Binomial CDF. I'm gonna just use a quick way. I'm gonna do alpha and the letter B. 4, 0.7, 2. So that will be 0.3483. Alright, so that will be the probability that is less than 3. So the inside this 0.3483, it has probability of 0 success, 1 success, and 2 success all added up together. Okay. Alright. Greater than equal to 17. So this is basically saying, this is another binomial. So this is basically saying, let me make this a little bit smaller. Alright, so this one is basically saying I got 18 independent trials, so that will be 0, 1, 2, 3, 4, comma, all the way dot 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 all the way up to 16, 17, 18. Let's go all the way up to 18 because I got 18 trials. So this one want me to do greater than equal to 17, greater than equal to 17. So what I want is 17 and 18. So the problem does not use an equal sign or the word exactly, so I cannot use PDF. I got to use CDF. But here's the thing about CDF. CDF, cumulative density function, is is adding up probabilities from the beginning, which is from 0 all the way up. So what I want is only the 17 and 18 on the back end. But the calculator is, if I do a CDF, the calculator will actually give me everybody before 17. So what we can do is use the complement rule. This is what I don't want. So what we can do in the graphing calculator is take the number 1, which is the whole thing, minus the probability that I don't want. 1 minus what I don't want will equal to what I want. So because what I want is 17 or 18, so here for my CDF, I got to say the number trial is 18, probability of success is 0.9. The number of success, what I wanted to add up is from 0 all the way up to 16, which is what I don't want again, but so I will subtract it from the 1. So here I will put 16. If you put 17 here, it will actually add up from 0 to 17 and then subtract it from 1. So that will just leave you with 18. So be careful, okay? This is the only part we can trip up on, is what number to put for the number of success. Alright. I hope that makes sense. And we've been dealing with problem like this throughout entire chapter 4. That's why chapter 4 tie into chapter 5 and so on. Alright, so this problem want me to find out greater than equal to 17. So what I want is 17 and 18. So to figure out what I want, we figure out what we don't want and subtract it from 1. And I have to do it this way because the CDF is actually adding up from 0 all the way up to the 16. So in my calculator, we'll type 1 minus second distribute, I'm going to say alpha letter B, binomial CDF 18 comma 0.9 comma 16. Alright, run to 4 decimal place, 0.4503. Alright. So a lot of this stuff, we actually already talked about it before, even before chapter 4. So I was hoping some of this will ring the bell a little bit. Alright, this one is greater than 1. So this one, the number trial is only up to 4. And the problem wants greater than 1. Greater than 1 does not include 1. So what I want, again, is 2 or 3 or 4. So 0 and 1 is what I don't want. Alright, so what we can do is to figure out what I want is take a 1 minus what I don't want, which is all the way up to 1. So number trial is 4, probability of success is 0.6, and what I don't want is up to 1. Okay. Minus second distribute alpha letter B 4 comma 0.6 comma 1. So that would be 0.8208. Alright, I'm going to show you how to do this in a different way, okay? Do it a different way. Remember the difference between CDF and PDF. CDF is adding from the beginning, which is 0 all the way up to a number. PDF is finding the exact one. So what I can do here is find exactly what I wanted, which is 2, 3, or 4, and then add them up by using PDF. So that's what I'm going to do. Okay, I'm going to show you how to do this, which you will notice is actually not as a good of a method, but it still gives you the right answer. So I'm going to do Binomial PDF. Alright, I'm going to find exactly what I want directly. So I'm going to find exactly at 2. My probability exactly at 2. And then I'm going to do another one, another Binomial PDF, do exactly at 3, do another one, Binomial PDF, find exactly at 4, and with these 3 answers I'm about to come up with, I'm gonna add them up, because what I wanted is these 3 scenarios. So second distribute, Binomial PDF, 4, 0.6, 2. That's 0.3456. If I do one with exactly at 3, second entry, I'm just going to change the last number from a 2 to a 3. 3, 4, 5, 6 again. Exactly at 4, second entry, 0.1296. Alright, so I found individual ones, so if I add them up, 0.3456 plus 0.3456 plus 0.1296. That will give me exactly the same thing as 1 minus Binomial Cdf, 0.8208. Alright, so there are 2 ways to do it. This is a little bit more work. Okay, sometimes this is a little bit more work. Alright, let's try another scenario. Though I don't think we've done this one yet. This is less than equal to 3. Excuse me, equal to 2. This one was less than 3. Alright, the keyword is less than. Okay, but this one has the equal to. So 6 trials. So my success can go from 0, 1, 2, 3, 4, 5, all the way to 6. What I want here is less than equal to 2, so that means what I want is from 0 all the way up to 2 this time. Okay, earlier when I do the 3 less than 3, I only count up to 2 because it doesn't say equal to, so I didn't count the 3. So here I count the 2 is because it says equal to 2. Alright, so that's what I want. So what I want is on the left side, which means the CDF will take care of it, adding from 0 all the way up to what I type in. So this is going to be Binomial Cdf. The number of trial is 6. Probability of success is 0.6, and what I want the calculator to add up to is 2. So I don't have to do 1 minus because what I want to here is already on the left side. Okay, so CDF is actually adding up from the left side. So Binomial Cdf, alpha letter B, 6, 0.6, 2. My answer 0.1792. Alrighty. Now let's try some these actual word problems. Okay, so those example I just did I just want to run through the scenarios with you. Okay, so let's do some actual word problem. you got to sense that this is a binomial. You got to sense the probability of success and failure from reading the problem. A researcher wishes to conduct a study of the color reference of new car buyers. Suppose that 60% of this population prefer the color red. Alright, so 60% want the color red. So that means there's the other 40% don't want red. There you go. So want red versus don't want red. And that is your success and failure. If 14 buyers are randomly selected, what is probability that exactly 9 buyers will prefer red? Alright, so no, my N got to be 14. Alright, my P, probability of success, got to be 0.6. 60% want red. Alright, and this problem wants me to find the probability of finding exactly, we want exactly to be 9. Do it that way. Exactly 9. So if I were to do what was shown from the previous page, I can move this. I can move this thing to the front. That's fine. There you go. Maybe that'll make you feel better. Move this to the front. Alright, this is an exact one. So PDF. Let me just go steal one of these. This is a binomial PDF. Number of trial is 14. Probability of success 0.6. I want to find exactly 9. Alright, so let's type it in. Second distribute. Choosing binomial PDF. 14, comma, 0.6, comma, 9. My answer. 0.2066. Okay. 20.66% chance. Alright, so what the answer is saying is about almost 21% chance that exactly 9 buyers will prefer red. Okay. 60% population prefer red. So if we select 14 buyers at random, out of those 14 buyers, what's the chance that exactly 9 of the 14 will prefer red? It's about 21% chance. It's real weird though if I would say, well, what is the chance that all 14 of them, the 14 I select, what's the chance all 14 of them will prefer red? A lot of people will say it's 100%, but nope. This is actually very, very little. E to the negative 4 means you gotta move the decimal to the left 4 times. So that is actually less than 1%. Okay, that's kind of weird. Because 60% of the entire population prefer red. I'm only selecting 14 out of however big this population is. So to get exactly all 14 of them prefer red is going to be very, very rare. Alright, so hopefully that kind of makes sense. Parents have always wondered about the sex of a child before it is born. So let's say suppose that the probability of having a male child was at 0.5, and that the sex of one child is independent of the sex of the other children. So what is the probability of having exactly 3 boys out of 6 children? Alright, so I can either have male or I can have female. So that's probability of success and failure right there. Alright, so it want me to find exactly 3 boys. A lot of people already thinking that the answer is a half, but it is not. Exactly 3 boys. Alright, so the probability of success is 3. Independent trials, it's got to be 6 children. I want 3 of them to be exactly boys. Probability of having a boy is 0.5. So that will be binomial again. PDF. Number of trial is 6. Probability of success is 0.5. Number of success is 3. I want 3 boys. So second distribute. Binomial PDF. My. 0.3125. 31.25% chance you'll get exactly 3 boys out of 6 children. It's not half. Okay, very strange. It's actually not half. Alright. Kind of strange. When you say half, that's referring to the number that is referring to the outcome of each child. Every child has 2 outcomes. Okay, every child has 2 outcomes. Either boy or a girl. So that's the half you're thinking about. Okay. But a half times a half times a half, alright, you know, it's just one of the many ways that we can actually have exactly 3 boys. Alright. So it's just like what I showed y'all here earlier about my free throw. You can have first 3 are boys, the other 3 are girls, so that would be one of the many ways. So you gotta realize that when we do binomial distribution, we are counting the number of ways something can occur. Then we times the probability of success and times probability of failure at the same time. Okay, so it's not gonna be exactly half. The half is referring to the outcome of each child. But since one child after the other, you got to multiply them. You got that sense into it. Alright, let's try another one. A certain insecticide kills 70% of all insects in the laboratory. By the way, you cannot have 100% kill. There's just no way. Okay? Alright? I mean, if you kill 100% of the insects in your house, that thing is very, very poisonous. So you probably don't want that. And you know some insects will eventually immune to the insecticide that you put on them. So let's say a sample of 8 insects is exposed in a particular experiment. What's the probability that no insect will survive? No insect will survive means that means all of them die. All 8 of them will die. PDF or CDF. No insect will survive. So that means I'm trying to find exactly 8 of them in my sample that will die. So the number of kills is going to be 8. The number of sample is 8. Probability of killing the insects is 0.7. So this is going to be a binomial PDF. N is 8. P is 0.7. And I want all 8 of them to die. second entry because I had a binomial PDF earlier. Eight. 0.7 and 8. The chance all atoms will die 0.0576. Okay, almost unusual event because this is slightly higher than 5%. So that's the chance all atom in the sample will die. Alright, let's say a fair die will be rolled 10 times. What's the probability that an even number, an even number is rolled less than 6 but more than 3 times? Ooh, that's interesting. Alright, so this is kind of weird now because you are rolling a die 10 times. You're rolling a die 10 different times. Every time when you roll a die, okay, you can either get what? You can either get even or odd numbers. So, what's the probability that an even number is rolled less than 6 times? So, let's take a look. Can I roll 0 even numbers? I can roll out of the 10 row. I can have no even numbers. I can have 1, 2, 3, 4 even, 5 even, 6, 7, 8, 9, all the way up to 10 even numbers. Okay, so this is what I can potentially roll. Okay, roll 10 different times, and I want even numbers. I can roll no even number at all. That means all 10 rows is odd. 1, 3, and 5. Alright, I can do this all the way up to 10 even numbers. This problem wants me to find less than 6. This is tricky. But more than 3. Less than 6. Do you count 6 to be less than 6? No. So that means what you want is 3 to 5. Okay. So this is ultimately what I want. 3 to 5. So how can I just find from 3 to 5? And this is where it's interesting. You got to be less than 6 but more than 3 times. So this is where it gets fun. So as you can see, what I don't want is 0 all the way up to 2. This is what I don't want. I purposely roll all the way up to 10, but if you really focus on, okay, what you wanted is 3, 4, and 5. What you don't want is 0, 1, and 2. So what you can do, alright, what you can do is figure out what you don't want and subtract it from 1. And that will give you what you wanted. But you can only go up to 5 though. Here's the thing, that you can only go up to 5. Because from 0 to 5 will include what you want and what you don't want. So you don't need the 6 all the way to 10. Okay. From 0 to 5 will get you what you wanted. They include what you wanted. So if I can figure out all the way from 0 to 5 first, and then subtract out what I don't want, that will give me what I wanted. Alright, so what we can do is to say binomial, oh no, let me write this down first. So this problem We can do this in a couple different ways. This problem is really long. Even numbers rule less than 6 but more than 3. So we are looking for got to be less than 6 but greater than equal to 3. Okay, greater than equal to 3 but less than 6. So if I write out the inequality, this is what it will look like. Alright, so I know my number trial is 10. Probability of success gotta be 0.5. Because when you roll a die, you're either gonna get even or odd numbers. Alright, so this is tricky. This is very, very tricky. I'll guide you through this, okay? If you want to do binomial CDF, your n is 10. Probability of getting even number is 0.5. But what is the number of success you wanted? If you go all the way up from 0 to 5 cumulatively, then what you gotta do is minus the binomial CDF of 10, 0.5, up to 2. Because what you don't want is from 0 all the way up to 2. So if the calculator can figure out from 0 all the way up to 5 and subtract what I don't want, that will give me what I wanted. It should work that way. Common sense tells us, you know, if you're actually trying to make sense out of it, it should work. So let's give it a try. Figure out from CDF, cumulative, all the way up to 5 first. Then subtract, second distribute binomial CDF 10, 0.5, all the way up to 2. Yep, 0.5686. Alright, so this answer is slightly off. Okay. Let's review the wording. Less than 6. This answer is a little bit too big. And the reason is this. Less than 6. More than 3. More than is actually using the symbol greater than. So if it's greater than 3, if it's greater than 3, that means I cannot count 3. What the problem is saying, see how easy it is to get tripped up on? What the problem is saying is it won't less than 6, more than 3. So what you actually want is only 4 and 5. What you don't want here is everybody else, but since I'm doing cumulative, I need to do it from 0 all the way up to 3. You see, just one number difference. That change it up a little bit. So we go all the way up to 5. That's correct. But what I don't want is actually all the way up to 3. So that will only give me what? That will actually only give me 4 and 5. Okay, figure out what I want, subtract off what I don't want. Alright, so I just got changing one number up. The first 5 is right, the second one needs to be a 3. That's the answer. 0.4512. So I wanted to show you that having one number wrong, okay, having one number wrong, that actually throw you off. This is very confusing because why is this number a 5? This number appear to be the same as that one, but this one is not 6 because if we go back to up here, I really want from what I really want is 4 and 5. Okay, less than 6, more than 3. So cumulative from 0 all the way up to 5 will have what I wanted. Subtract what I don't want is 0 all the way up to 3 cumulatively. Okay. Alright. That one is rough. This one is just as bad. A researcher wished to conduct a study of color preference again. 30% of population prefer green. So either I like green or I don't like green. So that's your probability of success and failure. If 10 buyers are selected, what is the probability that between 3 and 6, both inclusive, so I do include 3 and 6, buyer will prefer green? Alright, so I can have 0 buyer out of the 10 don't want green. All the way up to 10 prefer green. And this problem want me to find between 3 and 6 inclusive. So what I want is 3 all the way up to 6. Alright, so what I don't want is 0 all the way up to 2 if I do CDF. If I do a CDF, I can figure out 0 all the way up to 6, which that include what I wanted, and subtract off what I don't want. Now give me what I wanted. So this problem is literally what exactly, excuse me, it got to be greater than equal to 3, less than equal to 6. I got 10 buyers, probability of prefer green is 0.3. So this problem is binomial CDF, do all the way up to 6. Okay, 0 all the way to 6 minus binomial CDF from 0 all the way up to 2. So now will tell me what's between 3 to 6 inclusive. I'm just gonna second entry, just change it up some numbers. This is 2. Rather than 0.5, it's gonna be 0.3. 30% prefer green. 0.3. And it's not 5, it's all the way to 6. My answer 0.6066. Okay, 4 decimal place. Let's look at another one. Simple 17 light bulbs. If the number of defective light bulbs is 1 or less, it passes inspection. Suppose that 30% of the light bulbs are defective. What is the probability that it will pass the inspection? Interesting. If one, I got all the way up to 17 light bulb, 0 all the way up to 17. So I'm just going to say 10, comma, dot, 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 comma, all the way up to 17 light bulbs. if the number of defective light bulbs, 1 or less. So the lot passes the inspection. So you gotta be careful. This 30% is the same thing is referring to defective. So is this 1. So 0 to 17 defective light bulbs. Okay, that's the way how you look at it. You think about defective light bulbs. If it's 1 or less, so that means what I want, okay, is 0 all the way to 1. Okay, if it's 1 or less, it passes inspection. So what is the probability that it will pass the inspection? So this problem is actually going to be less than equal to 1. Alright, that's what we wanted. Less than equal to 1. I got 17 bulbs. Okay. Probability of success. Okay, it's not the success of passing the bulbs. I mean, passing the inspection. It's just is the probability of success of defective. So this 0.3, 30% means defective. I want to be less than equal to 1 defective bulbs. Okay. So that will be 0 and 1. So that will be binomial Cdf alright, 17 probability of being defective is 0.3. The number of defective I want is all the way to 1. Alright, let's type it in and see what we got. 17, 0.3, all the way to 1. So probability that you will pass the inspection, which is having less than, which is 1 or less defective bulb, is 0.0193. Alright, that's my answer. Kind of tricky. Alright, interesting problem. The last one. Okay, one more, then we'll be done. A student takes an exam containing 14 multiple choice questions. The probability of choosing a correct answer by knowledgeable guess is 30%. Okay, at least 9 correct answers are required to pass. You gotta get 9 correct out of the 14. Alright, at least 9 correct to pass. Ah, darn it. Oh, 14. I got 14 questions. So I need to at least get 9. So that means 9 and more. So that's 9 all the way up to 14. I will pass. Because the question is asking what's the probability of me passing. Alright, this problem is a little bit different because what I wanted is all the way on the very right hand. The other problem, what I wanted is actually somewhere in the middle. This is all the way to the right end, the back side of the whole problem. So if I find the probability from 0 over to 14, that's going to be 100% by using CDF. So what I can do to figure out what I wanted is take my number 1, which is the whole thing, minus what I don't want, which is up to 8. Okay. Alright, so this problem, what I want is greater than equal to 9. And I got 14 problems. Probability of guessing correct is at 30%. So this is going to be the whole thing, which is 100%, minus binomial CDF. The number sample is 14. Probability of guessing it right is 30%. 1 minus what I don't want, which is from 0 cumulate all the way up to 8. So 1 minus binomial CDF 14 comma 0.3 comma 8. The chance for me to guess it correctly, to get at least 9 or more right, is about 0.0083. So that's actually less than 1% chance to guess it at least 9 or more right. Alright, so hopefully you a little bit understanding of what we so call the binomial distribution, probability of success versus probability of failure. Alright, so this will conclude our video presentation. Okay, in the next lecture video we will begin to talk about the normal distribution, the bell curve shape again. Alright, thank you for